Introduce them.
I'll introduce you.
Cool, thanks. Are there people on Zoom? Like, we want to
Yeah.
make sure they can hear us? Or not?
I haven't seen anybody yet.
Oh, okay, well, in that case, I won't talk to the camera, there's nobody there. But thanks for coming, it's been a while since I've been here in person, since I've been a sabbatical. But today, Katie and Dylan have volunteered to give brief talks about their research. And I have to say, Katie and Dylan are usually amongst the first to, volunteer for these things, but it's really good for everyone to do these because it's like a very small, friendly environment. You can always invite anyone you like to come along, like you can invite your advisor or your lab mates or anyone too, or maybe you don't want them there and you get one there. So so it's intentionally a sort of a low pressure environment, but also these meetings have turned out to, because the Interfaces program has students from so many different graduate programs and so many different labs and disciplines. These seminars have often turned out to create collaborations between labs, sometimes even between labs where the investigators, the POs didn't even know each other. Feel free to ask questions, and the fact that your discipline may be different is fine. That's why we're here, to kind of learn how to do science in the interdisciplinary age. So Katie works in Albert Schau's lab, doing MRI and AI. So she's going to tell us about her this stuff.
Yeah, also, I'm also in Complex Lab as well, so, I decided that I have a big conference coming up in about a month, so, this is one of the talks I'm giving, and so I thought I'd try it out on you guys first. The title of my work is Simulation of MRI Case-Based Motion Corruption for Deep Learning-Based Artifact Detection and Correction, and I know that's a lot, so we'll go a little slow. All right, I guess. All right, there you go. So first we'll start with, what is cardiac MRI? Well, it's a very essential imaging modality. It provides excellent soft tissue contrast and high spatial resolution for imaging the heart. It doesn't just provide the structural information, it provides the functional as well. And that's what makes it kind of unique to some of the other imaging modalities. So for some examples here's what a more structural scan would look like. We also have 4D flow. You can see the hemodynamics, and this is strain, so it tells you a lot about how the function of the heart, and helps with diagnosis of diseases that cannot otherwise be determined non-invasively, so without having to actually pick them up. And all this is also done without any ionizing radiation. So this is the benefit over maybe something like CT. Okay, so cardiac MRI is great, but unfortunately, it comes at a cost, right? So it has very poor time resolution. So on the left over here, you have no artifact, no motion in these scans. It's I don't know if you guys can tell it's a heart, but it's a heart. But you can see over here, things get a lot kind of crazier. This is what happens when you breathe or when your heart moves. And unfortunately, those things are, well, I guess fortunately, those things are happening during the scan, right? So we want to be able to image even though the person's alive. And that's where MRI gets that's why sometimes CT is used. It's a lot faster. So these artifacts are not as severe, but you lose some of the functional information that you can get with cardiac MRI. So a big part of my work is, can we fix this or improve it in some way so that we can still get all the functional information that cardiac MRI provides without the artifact. Okay. So can deep learning, which is the main focus of my lab, assess and correct motion corruption? So why would we want to assess it? Well, quantifying motion corruption could be important because it can alert the technician if a scan needs to be repeated. The number one reason there's big problems with cardiac MRI is because the technician doesn't always know if the scan needs to be repeated. So a lot of the times it can be fixed, or at least you can get as much information as you need from it if you just change the scan parameters or instruct the patient to do something differently. That this isn't always so easy for someone to know, especially if they're not a physician. And so that's the main purpose of this work is, can we make an automated method to tell the scanner, hey, or tell the technician, hey, you need to repeat that. And this is very important because if they don't repeat it, they gotta bring that person back in, and that can be a month down the line. It's very hard to get scan time. Also, it's a pretty good way of measuring effectiveness of motion correction methods, so it'd be great if we just can correct it, right? If it's kind of difficult because we don't know what it should be, but if there was some magical wand that we can wave that would correct all of our images, I'm sure we would all take it. So, can we put deep learning to use for this? The main problem is, what's our ground truth? So we don't know what it should have looked like. No one can tell you what it should have looked like because the person moved. This becomes, difficult because we need, for most deep learning methods, you need what it should have been, what it currently is, and so it can learn the relationship between the two. So this is where my project comes in. So basically, what is happening when we have motion? Well, just like when you take a picture of someone moving, it's the reason it kind of looks like they're kind of blurred is because you're kind of acquiring data at multiple motion states. So just like that with MRI, these are different motion states of the heart. We're kind of like taking all the data, between each of these ones. So it's like as though for every line of data that we collect, it's at a different motion state, and it's all being kind of smushed in together. Now it's not quite like an image or like a camera, because we don't collect in image space, we collect in the Fourier transform, but I'm not going to go too far into that unless anyone wants to know. So if we can find a way to kind of combine this information, we can create or kind of combine these motion states into a synthetic image, kind of synthetic motion corruption, then we would know what it originally should have looked like, right? We created the artifact, so we know how to get back to the original one, but we have to make it realistic enough so that it actually is a good enough training set, right? So that's kind of where my project came in. So how we're doing this? Well, first, we need different motion states. If I can combine all the information together, kind of make this motion corrupted image, I first need the motion states, like the artifact for the motion states first. So there's two ways we do that. One is there's a type of scan in MRI called a cine acquisition. And basically the way that works is MRI, I kind of mentioned it briefly, is collected in K-space or Fourier transform. So think frequencies of an image, not the actual like pixels, but the frequencies. Basically what we do is we put an ECG on them, and we acquire a couple lines in the Fourier transform, and we put it into one image, and we wait, as the rest of the heartbeat goes on before we do it again for the next couple of lines. And we do this until we get the whole image. We do this for every single motion state. So you can kind of see how the purple all goes to one image, and it takes a while, multiple heartbeats, to get it all full, but it's kind of like as close as we're going to get to still, in that exact motion state. And the nice thing about it is also you get, like 20 of them. So we get it for every part of the cardiac cycle, well, discrete points, but yeah. Okay, so that's one way we can create motion states. The other way is, well, not all acquisitions are like that, because some are trying to measure different things. So another way we could do it, we should actually just apply deformations. So you kind of see it here, might be a little hard to see on the screen, but we actually just applied a 2D deformation to the heart and like abdominal wall and chest wall, so that it kind of created what we would think respiratory would look like. So the heart moves down and up kind of thing, and the chest wall moves up and down as well. And so these aren't perfect, but we think it would, we hypothesized that it would work, and I think we did it. So next, once we have the motion states, we need some way of combining it. So like I said before, everything is collected in frequency space. So what happens is in MRI, we collect a couple lines of the frequency space, and person moves, and now they're kind of like have a whole new kind of frequency spectrum, or so to speak. So what we decided to do is we take different lines of the K-space images or the frequency domain images, and we kind of combine them together. So we know that the way MRI collects it is one line at a time. And so what you'll notice is we could take a few lines of the first one, or it doesn't necessarily have to be in the right order, but a few lines of maybe this one and put it in the image, or in the K-space and basically replace different lines. So that every motion state is, or not necessarily everyone, but you have lines from different motion states. So it's kind of just like how somebody would be moving, what, that would basically corrupt K-space like, so. Let me know if you have questions, it's kind of, I know a lot. Are we good? Yeah, all right, cool.
Sorry, can I add? So
Yeah,
I'm not super familiar with MRI. Is K-space
for,
3 dimensions, 3 dimensions, or 4 dimensions?
well, technically all of them, but this project was on 2D, we have a project on 3D.
Okay.
But yes, it could also be done in 3D and 4D for the time dimension as well. So maybe just to kind of help clarify this a little bit more, what you have here, each of the motion states after I took the Fourier transform of them. And all I did was I parameterized this space so that I could create a lot of different motion artifacts with higher severity. So sometimes if I grab, if I borrow from more motion states or I borrow a lot from one other motion state, it's gonna make a lot bigger problem, right? If I mainly, maybe I only borrow 2 lines, then that's not gonna create as much of a problem, right? Because it also depends on where in the cardiac cycle I borrow from. If I borrow from a motion state that's pretty similar to my first, I'm not gonna see as much of a problem. So that's kind of what those parameters do, is they help me create something I can tune, something I can make very small motion artifact versus very large motion artifacts, because you're gonna see a whole range of them with people, so. I hope that makes sense, yeah. All right, cool. So that was the hard part. I think the rest is hopefully more straightforward. Okay, so how did it work? How well did it work? So here are actually, these are all synthetic. So, which, I know that you probably don't look at that many cardiac MRIs, but these were actually look pretty similar to what motion artifacts look like. And so we were very kind of surprised and happy to see that. So we created a way to, we can pick parameters so such that we can get a varying range of severity. So this one looks pretty close to the original. This one doesn't. And you can kind of tell that, this is using different motion states, because you kind of see like, it's kind of darker here, which if you remember, that's kind of looks more like maybe that one over there. So it's kind of combining maybe more of this and this together than just this one. And so it worked pretty well at creating the synthetic motion artifacts. It looks pretty realistic. And also same with this one. This, we did notice with so by the way, the first, I didn't mention this, but the top one was using the cine acquisitions for the motion states. The bottom one was using the deformations for the motion states. For the deformation one, we did get ranges where we can make it look less like realistic. So we actually kind of had to like find a good range of where it stopped looking normal. And that's because we kind of created these deformations. So some of the deformations were like not what you'd normally see the human body in. So we figured out that range and went from there, kind of thing. Okay, so that worked pretty well. So great, we can make synthetic artifacts. Can we use it to correct something? And that's the whole point, right?
Are those actually deformations or are they just translations?
We did deformations. Other groups did the translation, so that was like our first step. But we found that we really didn't see that much of a difference between them. And like the artifacts that they're either really weird because they basically just translated the heart like too far, or it was like you're nothing. It's because you kind of need, also like all the other organs moving too. So we found that really made a difference. Okay, so any other questions? All right, so next. Now is the CNN part. So we basically have 2 different data sets here. So the synthetic one, that's the ones I created, right? I took a bunch of regular images and I made a bunch of synthetic artifacts. So I know what they should look like. So we divided them into training, validation, and testing. The patients, like they're split. There's like no patient overlap. So if a patient's used for the training, they're not used for the testing. That's our first data set, which I'll show results for the testing stage of it. And then we also have a real world data set where radiologists went and scored these images. So in a lot of past work, people have actually scored images and tried to train neural networks on that. But this can be very time consuming, and every single acquisition, you got to retrain. And if you can imagine, what ends up happening is it really doesn't end up implemented because we have so many different types of acquisitions in MRI. And also so many different body parts as well. Okay, so any questions on this? I can go into the architecture more if anyone's curious. It's mainly it's actually a multitask network, so it does two things. It actually corrects the image. We found that it actually was helpful to do that too, as well as scores it. So the original, this was actually a project funded by GE, because they want to be able to score images. And so we originally just started with scoring, but we realized that actually trying to correct the image actually kind of helped us too. So, okay,
I have a question.
yeah.
Do the radiologists score based on the corrected images or do they do the like?
They're only looking at the, so these real world data set, we don't know what the original images look like. So sorry, let me say that again. They're like,
Gold standard.
yeah, they're not the gold standard, so they're like artifacty. So if somebody's breathing in there and their heart's moving and stuff like that, so basically the radiologist just looks at them and says whether or not there's an artifact or not, and it could be a wide range of them. So some don't have any artifacts, some do. With the synthetic data set, the original data that we started with, that was all gold standard. There had to be no motion so that we could get individual motion states, right? And then I corrupted it. So that's the difference between those two. Does that make sense? Or, yeah.
For the real world data set, when the radiologists score each slice, is there any cross check between the experts that are scoring them, or is it just one?
We plan to, right now it's just 21, yeah, mainly my advisors. You just did it like on a Saturday. So the goal is to get two more, but yeah, it's a good one. Because the one thing you will see in other, like especially other people's projects who have tried to do this with a radiologist, there is a lot of differing, like opinion on the score. Just because it needs to be super, well, for one, it's kind of hard to tell, you have to have really good criteria on what is a 0, what's a 3. And then also, even like, just if you have the radiologist rescore again and not tell them, there's like variability. It's kind of interesting. It kind of depends on how tired they are and stuff like that. So it's also not a perfect method. Okay. So this is on the synthetic test set. So remember I had, I held out some data that I synthetically generated that we did not train or validate on, and just to see how well this works. So I do know what the ground truth is for this. And so on this side, we have the artifact scoring. So the bottom is the actual measured difference. This is an SSIM score, by the way. So the measured difference between what I created and the original data. So this is what the true answer is. And then this is what my the neural network predicted. And it did a pretty darn good job. And also you can see that we have like identity. As you can see, it's primarily actually lining up well with the line, as well as we did kind of have a lot more over in the higher range. So like a higher, like I should be a little careful here. The higher range means like a score closer to 1 means there's very little difference between the images. This is an SSIM score. So the reason we have more data up there, where like meaning very little difference, very little artifact, is primarily because we actually had this data was on like patients in UC Health. And so actually a lot of them had heart conditions that made their heart not move as much as like, a normal person. And so if there's very little differences between their cardiac motion states, I can't create larger, artifacts. So may want to go back and try this again on a maybe, it's kind of hard to get like healthy subjects all the time because it's, who's getting a cardiac, workup is somebody who most likely has a cardiac problem. But actually we found that it worked pretty well on our held out data set, so it may not be necessary. But that's in case you're curious why the majority, we have so many up here at 1, and that's why. Any other questions? Okay, so the other side is the artifact suppression. So this is how well did it correct it. So before correction is the SIM score. Remember, 1 means no artifact. And after correction. So you can see that there's a pretty significant difference for the two acquisitions that we had. So that's good, it's correcting. We did find that it did a better job on the MDE data. We think that's because that used deformation, so it may have kind of learned, I don't know, necessarily like the more synthetic kind of motion artifacts, the synthetic motion states than maybe they did with SSFP, but kind of have a hard time actually really checking that because, we can't really do it with real world data, right? But this is pretty promising that it is correcting it. The SIM scores are getting better. And yeah, so it's removing some of the artifact. Any questions on that? All right, cool. All right, but now my favorite part. Okay, so this is the real world data. This is the stuff that matters, right? We can't just check on synthetic data. So basically what you're looking at here is this, we'll just start on this side. These are the scores by slice. Okay, so none up here, is like basically saying there's no artifact, where severe is the worst, so the lower, more severe, and the same kind of scale for the predicted SSIM. So this is basically what the neural network predicted. And you can see it really lines up pretty darn well with the radiologist, is great. And we saw this on most of the actually like most of the real world data sets, that it's just lining up really nicely. And you can see here some examples of what these images look like. So there's very little artifact in this one, and then you can see with this fifth slice, you can really see the artifact here. It might be, I don't know, if you guys can all see it back on the Zoom or not, but yeah, you're seeing a lot of blurring. And it's really difficult to actually see where like the heart walls are. And again, it goes right back up to being pretty nice, good looking slice. So it seems to be tracking something pretty well. And here's an example on the MDE data. So this is again, the real world data. You can see that it's the artifacts. It's a little hard to see on this, but it's blurrier. Blurry is one of the artifacts that we see with motion, just like with taking a picture of somebody moving, you'll kind of see them blur, right? But this is still not too much of a difference if you really see it on this one. So you can see it almost doesn't look like a heart anymore. So yeah, it's definitely a worse artifact. And you can see that it's scaling pretty well too, right? Like this is 0.7, this is 0.75. So it is getting that this is not as bad as this one, but it's still worse than this one. And so that's nice to see. And it's matching pretty well with our radiologist's grades. And then also we decided to see, okay, well, can we use this to actually tell the technician, hey, either rescan or keep going type thing, because that was the real goal of this project. So just looking between severe versus not severe, that's really the two categories we care the most about. It has a pretty good like AUC. So basically we able to pick a threshold, right? Where you say, okay, any predicted SSIM score above this threshold is fine. Anything below it, not fine. And then you can see here what the true positive rate versus false positive rate is. If we pick those points. So that's what the ROC analysis does. And our optimal value is the red, or the optimal threshold is the red. So that will has a pretty good basically true positive rates versus false positive rate. So we want to make sure that we don't just say scan it or don't scan everything, or do rescan everything, right? And also on top of it, we noticed that there's pretty good separability between the different categories. So these were the categories that the radiologist had made. So no artifact versus severe, and the individual ones as well. So it doesn't do quite as well of a job here, because I guess it's a little bit difficult that, between no artifact versus mild versus moderate, but you can still see this separable, and it was like with the significant, it was pretty significant too. So the p-value I think was 0.001 or higher or lower, so which is what we want to see.
Is it significantly different between each one of the,
Yeah.
between the moderate and severe?
It is, yeah. Yeah, it was, so the best one was the one you're seeing, the blue box versus the severe. That was like 0.0001. But the other ones were also significant, so all less than 0.01. I can't remember the top of my head, but they were all less than 0.01. The p-value on each one. So like between no artifact and mild, no artifact and moderate, like every combination.
Just to understand the problem, like, for the doctor, is it important to separate the severe from non-severe, or is it like important for prognosis purposes to understand the improvement?
Okay, I see, yeah. So I would say the biggest thing we wanted to solve with this was that actually to tell a technician, hey, this is severe versus not severe. Because that's just going to tell them whether to rescan. Most of the time, I mean, the technicians here are fantastic because they're all trained by Albert, my PI, on how to do cardiac MRI, but that's not the same everywhere. And so a lot of the times that's the biggest hurdle is that the doctor will get the image and be like, I can't read this. And then they just have to rescan. Now, it's also good to sometimes be able to know the difference between mild, moderate, and severe, but I'd say that that's kind of just like a benefit. Like, I would say most doctors probably would see that and maybe would read it a little more carefully. Like, if they see that, oh, there's a moderate artifact, and to me, there doesn't look like one, I'd just be a little careful. But I don't know, that's a little less, I think every physician would kind of have a different opinion on that one, whether or not they change their mind based off that. I don't think so. So, yeah, any other questions?
So another way you can, well, once you get this far, and one thing you can do is you can then present this prediction back to the
Mhm.
physician,
Mhm.
and they can then say whether they agree or disagree.
Yeah,
And then you can use that data to update.
yeah, that's what we're currently running, yeah. Exactly, yeah, actually, I just got that, we just had that idea as well, and, so Albert's back to scoring then. But,
Because it could be that, particularly it looks like the difference between 1 and 2 might be it might not be very big. In other words, it might actually not be very easy for
Mm.
even the experienced
Yeah.
observer to actually distinguish between a 1 and a 2.
Mm.
And so it could be if you told them what you thought was a 1 and a 2, they might just agree, like it's not worth arguing because they didn't really have a strong opinion
Exactly.
either way.
And then also, I mean, Albert's not here, so I can tell you guys this. But a few times, right? Like there was a few examples. He went and we scored it, and it really did not match his scoring whatsoever. And we were like, what's going on? Especially because we had so many good results, right? So we went back and I gave it to him, like, can you rescore this? And he did. He agreed with the algorithm.
Yeah.
I was very happy. But
And I think that's a real
yeah.
issue in this type of thing where you're using subjective
It's also-
assessment as the gold standard.
he also said it was slightly based off of how, when he just ate lunch, when he did, how hungry he was when he did and how much patience he had left.
Well, for the audit matter, like you can spend a lot more on the first one than the last one.
Yeah, and also I have a feeling that like if you spend a lot of time on one, the next few, especially if you're running out of time, you're gonna get frustrated. So it's like a thing. Obviously, he's pretty consistent. I would say he didn't do this type of, we didn't like actually have him, rescore to see if he can match his first scores, nor do we have another radiologist score. But we have done that for other data sets, and his is pretty consistent generally, so we plan to do that with this one as well, so that we can use it for the paper. Just to, actually call this the ground truth. But yeah, but no one tell that to Hal, even though this is going on, he'll never watch it. Oh, sorry, yeah, okay, I'm almost done, so these are just some of the correction results. So we actually do see a pretty good correction, so these are some of the artifacts that you see. You can see that it's removed here. With any of these things, is it right? That's a big question. Because, I think, you can end up erasing or smoothing out something that is important, so the idea behind the correcting is more. It was more to support the scoring, but also this is something we would show in addition to the image. You can see both. You can make the decision whether or not that little piece that got removed was important. Because I think, no one's gonna know for certain that this actually was, what it should look like. But some nice things is you actually can see some of the like the valves a little bit better on the corrected image. So that's nice. Also, it's a little hard to see here, but a lot of the blurring artifacts have been removed as well, so. And I'll go through this kind of quickly, but so our conclusion is realistic motion correction can be synthetically generated using this kind of simulation technique. And a wide range of motion severity can be simulated using this method to better train deep learning based artifacts for detection and correction. And my future work is to finish the 3D abdominal images that we're now working on. So, yeah, thank you to the training grants and as well as my lab.
Okay.
Oh, you weren't recording?
Not for that little bit right there.
Okay,
Alright.
Cool. Right, so I'm Dylan. I think most of you have met before. So I'm a student in mechanical engineering and really specifically in control engineering. And so probably maybe some people, but not everyone has heard about what control engineering is. And certainly there might be questions on how this is related to biological applications. So I'll try to give a rundown of that. And then hopefully I'll have enough time to actually talk about some of the algorithms we've been developing in the lab. Um, so that outline today is, yeah, I want to talk a little bit about what control engineering is and really where I think these algorithms that have been used in control engineering can give us insights into pharmacology. The main algorithm from control engineering that I'm going to talk about is this thing called Hamilton-Jacobi safety analysis. So I'll give a rundown of that. And then we have these like two major classes of methodological advancements that I'd like to touch upon. The first is these are basically, this algorithm was really developed more for traditional engineering applications like robotics. And certain things come up when you go from robotics to biology that need to get fixed. And I kind of group them together to these two sets of problems. One is complex tasks and toxicity prevention, where I think we've more or less solved the problem, which is pretty cool. And one is on scaling to larger models. So robot models tend to be pretty small, biology models tend to be pretty big. How do you handle that? And I think we've made some good progress there. It's not solved, and I don't think it ever will be finally like totally solved, but I think we've made progress. So hopefully I can talk to you about all these things. Before I do though, I just want to give a lot of thanks to like everyone associated with this work. So Sylvia Herbert is my Innovace's technical advisor. She worked under the person that developed Hamilton-Jacobi safety analysis. She's the reason I know about the algorithm. Jean Zhang is in pharmacology. This project is obviously very pharmacology related. Sylvia is not a pharmacologist. It's very helpful to have someone who knows about the biology end of things, and she's been really kind to let me sit in on lab meetings and have discussions with her about the science. And then Boris Kramer is my other research co-advisor, and he works on model production. He's also in mechanical engineering. And a lot of the algorithms you'll see today are model production related. So, and then most of all, of course, I have to thank interfaces. So none of this would be possible without interfaces. Almost all of the grant money for these algorithms goes towards robotics. So it was cool to be doing something that was more medicine focused, and that this just would not have happened otherwise. Okay, cool. So first off, I just want to give a really quick rundown of what control engineering is. And basically what control engineers do is we design algorithms for dynamic decision making. And those sound like probably pretty loaded words, but I mean them very specifically. So let's be concrete here. If you've ever turned on cruise control in your car, you are using control engineering. It's an algorithm that says, how fast am I going now? How fast do I want to go? How much should I apply brake or throttle in order to be going the speed I want, despite things like wind or uncertainties in the environment. If you've ever taken a commercial airliner, you can thank control engineering for getting you to your destination. Basically, everything that you do between takeoff and landing, so other than like literally getting off the ground and getting back to it, is done by a control algorithm that runs the plane. And process control, if any of you are chemical engineers or have chemical engineering backgrounds, you probably have to take process control class. This is the chemical engineering version of control engineering, which is the one that's going to be kind of most relevant to us today, because we're basically going to think of the body as a giant chemical factory. These are very traditional applications of control engineering. These days, control engineering has kind of exploded largely due to AI. So if you all have seen this like documentary, this is probably from 10 years ago now on Netflix. There's this documentary about how the Google Mind team developed an algorithm that beat the world's best Go player. That was all done with reinforcement learning, which is control engineering plus machine learning. And so self-driving cars use control engineering, and most of all, autonomous robots these days are one of the big focus of reinforcement learning and control engineering. Okay, so where does this come into play with biology? And it turns out many decades ago. So I actually, probably most of the people in this room have heard of the term systems biology. What probably most people don't know is that that term came out of the control engineering community. So this was the first instance I could find in the literature of the term systems biology was from this conference on systems theory and biology. And I think this quote from this conference book is actually really cool because they're talking about Norbert Wiener, who's like one of the original control theorists. And they're talking about, they say, the use of systems concepts in research in the life sciences has grown apace. Such concepts have been of increasing value in the study of neural networks, respiratory system studies, and studies in that's the study level. And so particularly with regard to the neural networks, what they're referring to, I think, is the Hodgkin-Huxley models. And so these very early models that have eventually given rise to a lot of the neural network models we use today in the AI field. So kind of just a cool factoid about systems biology. Probably if people are in bioengineering, you may have seen this book before. This is kind of the modern treatment of systems biology. And this is kind of the models we'll be talking about today. These are differential equation models describing how compounds in the body or in the cell change over time. So if I have some transcription factor X that regulates a gene that produces a downstream protein Y, I can model the way that the concentration of the downstream protein changes as a function of the upstream protein. This is like very simple differential equation. And once you have differential equations like this, you can talk about transcriptional networks, so ways in which transcription factors, you can imagine maybe Y is also a transcription factor for another gene, and maybe there's actually feedback between these things. And these transcriptional networks have functions in your cell, like memory, like signal processing, like time sensing, and then they connect together to form these larger modules that have higher level behaviors. So this is kind of the perspective about feedback control in biological systems, and we have this paper on this that I really like, and I would love to talk to you more about. So if people are interested in this idea of like, how do we look at biological systems from a mathematical point of view, please grab me afterwards. Unfortunately, I don't have enough time to talk about that. So what I'm going to talk about is on the right, which is most of the work we've done relating these things, which is really feedback control for biomedical applications. And really the question we're asking here is, let's say I have a model for a disease or a treatment process, what do I actually do with that? So we're spending all this time and money creating these models, whether they be machine learning based models or differential equation based models. But what do you actually do once you have a model? And so hopefully we'll answer that question in one specific context, which is quantitative systems pharmacology. So QSP is the study of pharmacological models, so models of both diseases and treatments. And it's composed of two parts. So there's pharmacokinetics, which describes what the body does to a drug. And then there's pharmacodynamics, which describes what the drug does to the body. So for the first one, think about things like metabolism. For the second, think about things like protein activation and phosphorylation. And these are mathematical models describing both of these processes put together. And this QSP is kind of a field that started out in academics, but these days it's very important. So if you want to work at GSK and you have a PhD in applied mathematics, you can apply to be a quantitative systems pharmacologist there. If you want to stay in sunny La Jolla, you can do the same at Pfizer or Merck or Takeda. And you might ask, why are all these companies now investing in hiring all these people in quantitative fields? And obviously there's good scientific reason for doing this. There's also good regulatory reason. So the FDA is now updating its guidelines to say that they're taking evidence based on modeling and simulation. This is at the moment largely for medical devices, but my understanding is they're moving towards this in the pharmacology space as well. So these companies are really invested in building these models. But the question again is, what do you do once you get to that, once you have a model? And so for a second, let me talk about how that works in a robotics context, right? So in robotics, we actually have models already. They're really simple models. They're F equals MA kind of models. And so then you design these algorithms. And the point of these algorithms is to say, okay, I take in the model as input, and I'm going to figure out something important to achieve my robotic task. So let's say I have a drone, for example. This model is x dot equals f of x u d. Here x is the state, u is the control, and d is a disturbance. So u is like things like the motor control or motor torques in the robot, and d would be things like wind. And this algorithm called Hamilton-Jacobi safety analysis takes in this model, solves this partial differential equation for something called the value function. And then once you've solved this partial differential equation, you get the optimal motor control for free that tells you how to control your robot. And that seems really unrelated to us until you think about what these PK/PD models look like. So in these PK/PD models, you have, again, two sections, the pharmacokinetics and pharmacodynamics. So let's say I have a three compartment PK model with two drugs that I'm considering, drug A and drug B. And then I have some downstream protein, which can be phosphorylated or unphosphorylated. And what the drug does is it changes the protein state between the phosphorylated and unphosphorylated state. I can rewrite this by shoving all of these dynamic quantities into this variable x. I can take the rate at which I supply the drug to each compartment as u, input, and I can take the things like parameter uncertainty that I don't know and shove this into this variable d. What do I end up with? X dot equals f of x u d, just the same as robotics. So if I were to apply Hamilton-Jacobi safety analysis to my PK/PD model, Now I have this 3-compartment PK/PD model. I want, instead of having goal states and obstacle states, I have therapeutic states, so states of the phosphorylated protein I want to reach, and also toxic states, so states in each compartment that I really don't want to get to due to overdose risk. And now if I solve that same partial differential equation, so again, the math doesn't change at all, but I get, instead of the optimal motor control, is the optimal dosing regimen. So it tells me how much of each drug to supply to each compartment at each time in order to reach the therapeutic state while avoiding the toxic states. And I just want to talk, so like the idea of this is to scale up this algorithm to be a general purpose algorithm, and work on very large, complicated models, especially with combination therapies. It turns out that even in very small PK/PD models, sometimes HJSA finds things that are kind of cool and unintuitive. So here I have a really tiny model. This is 2 compartments, just blood and tissue, 1 drug, and 1 protein. And the whole point of the drug is it just upregulates production of that protein. And so if you go to a doctor and you get treated for anything, probably what you're going to do is you're going to take a constant dose, right? So you'll take 20 milligrams of some pharmaceutical every day for a week. And if you were to do this, take this constant dose in this very simple example, you would eventually reach your therapeutic goal, but you're going to have toxicity issues in between. Now, the other kind of treatment that you'll frequently see is very aggressive doses, where I give basically as much dose as the patient can tolerate per unit of time for as short a time as needed. And it turns out that this does a lot better in this example. You still barely hit the toxicity level in the tissue, however. But if you give this to HGSA, it'll figure out the optimal dosing regimen. And so what it'll do is it'll actually say, let's give you an aggressive dose for a small amount of time. Let's then back off in order to give time for it to be the drug to be metabolized in the tissue, so you don't reach toxic thresholds. And then we're going to give you the drug again in order to get you to your therapeutic goal. And so this allows you to get about a 10 to 20% decrease in toxicity while getting you above the therapeutic threshold. Okay, cool. So hopefully I've just convinced you all that we have a bunch of models from these companies, and also there's an algorithm that basically gives us the optimal dose given on these models. And that seems like we are done, right? Not so much. As I mentioned, there are big differences in applying this algorithm when you're doing it for robotics versus for biology. So the first one is that, unlike in robotics, this algorithm is going to try to outrun toxicity. And this has to do with a very kind of nuanced mathematical fact. And it was not immediately clear how you could actually fix this. But it turns out the way to do this is with this task decomposition algorithm that hopefully I can touch on in the time now. And then the other problem is that it's intractably slow for these large models. So often QSP models are on the order of 10 to 30 states rather than robotics models, which are talking about 3 to 5 states often. And so this is just completely intractable. Like HJSA won't run on models this large. But we have 3 approaches that allow you to do model reduction at various scales. So the first is kind of related to the math used to do to derive the Michaelis-Menten or Hill functions, which is based on this map called singular perturbation analysis. Probably not gonna have time to talk about that. As I talked about, Boris Kramer is a faculty in MAE who has all these ways of simplifying these complex models. So we've used some of his algorithms. And then I think, to me, the most exciting thing is the use of deep reinforcement learning, which is kind of this third class of reinforcement learning, of machine learning, on top of supervised and unsupervised learning, that is really specifically meant for these kind of problems. And we've seen like huge progress with this to the point where I think we're kind of ready to start on these kind of 10 to 20 degree of freedom models that we previously couldn't. And then hopefully I can talk about some of the plans for applying this. So at the moment, we've kind of finished the methodology stuff and we're moving on to just applications. Okay, so as I mentioned, one of the most annoying things with applying this to biology models is that the algorithm will try to outrun the toxicity. And this has to do with the fact that in robotics, the targets are already a priori safe. So long as I make it to a target, I can basically ignore what happens afterwards. But in pharmacology, that's not true. So I could make it to my therapeutic goal. Often that's what happens if you take a large dose of medication early on. But you have to worry about downstream toxicity. So you don't want to overdose the patient. So this is not something that's like an academic problem. This happens actually all the time. So this is as simple as of a PK/PD model as I could basically come up with. You have a drug, it goes into the blood, it gets processed by the kidneys, that's it. You want to reach your therapeutic threshold while avoiding the toxic one. And this is what HASA tells you to do, which is to take way too much drug, so you get way over the therapeutic threshold, but you do cross your toxic line. And it's very clear you could avoid the toxic line by just taking less of the drug. So to solve this problem, we developed this algorithm, which actually may seem a little hacky at first glance, like what are you doing here with all these diagrams? But it turns out this is the optimal way to solve the problem when you actually care about what happens beyond what you, when you reach the target. So if we actually mathematically can show that this is the right thing to do. And so if I apply this to my very simple example, what I see is HASA automatically does the correct thing. It gives me just enough of the drug while avoiding toxicity. So this is a very simple contrived example. You might ask, why not just stop giving the patient drug as soon as they hit their therapeutic threshold? Like, why do I even care what happens after that? Turns out that's not good enough. So this was just an example we had from the paper where we solved this problem, where we show that even if you are to stop dosing as soon as you hit your therapeutic threshold, you still can run into toxicity issues if you don't use this correction. But with this correction, we've been able to solve this problem. And this kind of complex task compositional approach has taken on kind of a life of its own. So if any of you have met Will Sharpless, who was a previous interfaces student, this is now the main focus of his PhD. So he's figured out how to use these kind of same algorithms for doing all sorts of complicated tasks. I'm not going to talk about those because I want to get to some of the reinforcement learning stuff. So these are various, I'm going to skip over these things in the interest of time, but these are various ways that we can apply these to larger, more complicated models. But what I really want to get to is, in the time we have remaining, is reinforcement learning. So probably most people, especially if you've taken the interfaces machine learning course, have heard about supervised and unsupervised learning. And these are the two kind of subsets of learning that we normally use in biology. So Katie today gave a really great case study on supervised learning, specifically for imaging. Probably most of you have heard of K-means, which is unsupervised learning. I had not really known what reinforcement learning was till coming to UCSD. But basically, this is a type of learning that instead of having supervised or labeled data, it looks for rewards in the environment. So this mimics kind of how animals learn or how humans learn, which is based on reward signals. And basically, the goal of that algorithm is to maximize the total reward seen by interacting with the environment. And this is how DeepMind learned how to play Go. This is how a large number of the advances in robotics happen nowadays. And it turns out that what these reinforcement learning algorithms do is they just really efficiently solve that partial differential equation I showed you at the very beginning. So we published a paper on this where basically we used reinforcement learning to solve the reach always avoid problem. So this is the problem where you actually care about what happens after you reach your target in a variety of examples. And what we've been able to show is that this approach learns a lot better than the traditional algorithms used in this field for solving safety problems. And the way it works is basically you separate the problem into two different ones. Your upstream problem, which is I want to do, I want to get to my goal and not get to some toxic concentration after that. And then you also simultaneously learn just how to avoid toxic concentrations. And you bootstrap these estimates into one giant composed policy that tells you how to do both things. And so these were kind of standard benchmarks that we needed to show we could do well on. But I want to show you what this looks like on a pharmacology problem. So this is an example of a problem where I have two drugs and they have some interaction. So if I have high concentrations of both drugs simultaneously, it leads to increased toxicity. And this is a 7D model. This is way too high for us to solve with traditional methods. Like if you were to try to solve this with a normal PDE solver, you'd have to solve an 8-dimensional partial differential equation, which just can't be done on any sort of at least small laptop. And now we can do this in about 5 minutes, maybe on my local machine. And so what this algorithm is learning how to do just by trial and error is figuring out actually because of this toxicity effect, I need to separate the dosing to make sure that I'm only giving drug one. Sorry, I don't have my cursor, yes, but I'm only giving drug one when drug two is at low concentrations and vice versa. And so now with this, kind of these methodological improvements, we are moving towards application case studies. So the first step is going to be to look at published QSP models in the literature and figure out the optimal, show we can figure out the optimal dosing regimens for these already published models. And then I'm interested in collaboration with the Zheng Lab in developing some of our own models for new processes where we have data on them and kind of showcasing this new method. So the idea is this is supposed to be a very general broad method, but we want to showcase it on realistic QSP models now. So sorry, I know I was going really, really fast so that I could get everything done in time, but hopefully I gave you kind of an overview of what I'm trying to do in this project. I'm happy to take questions. These are the publications associated with this work at the moment.
I have a question. So wait, what do you mean by deep reinforcement learning? I mean, I know reinforcement learning, but is it like?
Yeah, that's a great question. So reinforcement learning, like just like supervised or unsupervised learning, you don't need neural networks to do reinforcement learning. Like reinforcement learning means you're doing reinforcement learning with an algorithm that involves a neural network. And basically,
To just training it to learn state, but
yeah, so if you remember, it's very similar. So Dr. McCulloch presented on physics-informed neural networks during the ML class. He gave a lecture on these, and it's a very similar idea. So you're using a neural network to approximate the solution to a partial differential equation. In this case, it's that partial differential equation I showed at the beginning. And so instead of explicitly solving the PDE in like a CFD like solver, like you usually do in engineering, what you're doing is you're actually training a neural network that approximates the PDE solution variable.
You still count as reinforcement learning though?
It is reinforcement learning because the way it works is slightly different than PIMS. So they this algorithm is actually like under the hood. What it's doing is it's trying a bunch of different dosing regimens.
Okay.
It's seeing which ones work better and worse based on the reward signal. And then the ones that work better, it keeps on focusing more and more on. So
I guess that is true.
So you use the differential operator to generate your error, but you don't actually have to like solve the PDEs in advance and use the solutions as for a supervised training. You might find it interesting. Various people now are starting to use an old technique called bond graphs. That was developed in the 60s at MIT to formulate large systems biology models. And the nice thing about bond graphs is they reduce everything to energy flow. So you can take so these are for where the equations actually represent physical processes, like they might represent chemical flux or they might like in a chemical reaction network, but then there might be electrophysiology, so it might represent current flow, or there might be some mechanics involved, so they represent momentum. You can have a sort of unified way of combining all these different types of process and physiological models. If you express everything as a energy and a power relationship, basically, and that allows you to put together models, physiological models that have chemical fluxes and maybe electrophysiology and maybe mechanics and metabolism in a consistent but also practically automatic way now. So people have developed these large bond graph models, and since they're sort of grounded in physics, and they typically combine like biochemical reactions with other things like mass transfer or electrical ionic fluxes or mechanics. They might be interesting test cases for this type of strategy.
No, that sounds really, really helpful. I think one of the things we've been interested in is like what models are the best thing to showcase these algorithms on. These are very general purpose, and for some models, they'll find things that are genuinely novel, and for some, it's just going to say use a constant dose, right? And it'd be nice to
QSP is a good example, but sometimes the QSP models can be a bit arbitrary. In other words, they actually violate, thermodynamic principles because no one ever sort of explicitly forced them to satisfy the kind of empirical models. They're empirical models that are based on equations that are based on mass conservation, but when they put them together, they don't necessarily explicitly enforce mass and energy conservation. Whereas if you formulated the same type of model with bond graph, it would. So rather than you doing it, you can just find that people like Peter Hunter have started to build quite large ones
Cool, no, I appreciate that.
in big libraries often too.
I'll look into that. That would be a cool, yeah, be a cool testament.
I have a very naive question. How do you sort of validate your model?
Yeah, I mean, so we're a very computational lab, right? So without IRBs or people that know how to do experiments, it's going to be very hard. I guess the thought for me on this is that I'm actually more interested in using these things for hypothesis generation than for like clinical workflow. So you could imagine doing either, but often by the time you've gotten to the clinical setting, you kind of know which drug you're going to use. You have a decent idea of how much time you want to give it to a patient for. These are things where maybe I have like some set of drugs that I'd be considering a combination therapy with, or maybe there's not even a drug developed for your disease process yet. And you won't say, I think I can target this thing. Is it actually going to help me to include it as a possible target? And you can run this algorithm on it and see, oh yeah, actually, if I focus on target 1 for 1 week, and then I focus on target 2 for a second week, you get a much bigger effect than focusing on either one individually. And based on that hypothesis, we should actually be thinking about like actual drug targets we can use to suppress or inhibit these proteins and test this hypothesis. So I think there's both the clinical utility to this where I think it's a little more far-fetched, I don't know, but I think maybe it's more on the research side for hypothesis generation where I try it first.
I remember when you set up your model, you talked about having like kind of like similar to the control, where like you think about like both I don't know, what was it like? I guess my question is this: what is this like on a subject per subject? Can it be on a subject per subject basis? And would that even be useful?
Yeah, totally. So if you are able to measure things about an individual patient, you can configure the pharmacodynamic parameters like K1 and gamma 2 and things like that.
Yeah.
And because
So when you guys did it, you guys just set that to like something standard.
yeah,
Okay, that's what. Yeah.
but for an individual patient, you could do that. And then the cool thing is we never really know these parameters.
Mhm.
You can include disturbance terms like model
Yeah.
disturbance. And then you can actually see like if I even let's say I know my drug treatment already, I know exactly what I'm going to do. I can figure out what's the worst thing that could happen. What's the thing that would go most wrong based on this algorithm as well.
But I guess, do you see that ever being like, I guess you're always gonna have to do this kind of like on average for the average population kind of thing, right? Because if someone's gonna use this to say what they should do with their drug, that's what they would have to do.
Probably,
Do
yeah.
they, I mean, and you guys just, I guess you kind of already said this, but you didn't try this on like a specific example, like where you set those to something.
Right, these are really stress testing examples, like the one you were seeing here. These are things that I cooked up to showcase why we need to develop these new methodologies.
Mhm.
When you like in the literature, they'll have have the specific PK parameters that are estimated, but those are still estimates, right?
Yeah.
These are not. It's really hard to measure a lot of these things in a specific patient.
So, yeah.
I have a question,
Mhm.
it's right or wrong, but normally when you have a drug, since you have a gut, I assume you take a pill, you normally have first pass and you have second pass and you lose.
Yeah.
So are you just looking at the first pass and
Yeah, that's a great question. So like some of these models, specifically models that are called like physiologically based pharmacokinetic models, will take into account really detailed things like portal system kind of deals. For the most part, models used in clinical pharmacology are like 1, 2, or 3 compartments, and they often ignore that. What they will do is they'll include a correction term for the bioavailability, which is basically like how much of the drug actually makes it past the liver. Yeah,
There are also prodrugs that actually have to be metabolized by the liver in order to produce the therapeutic compound.
yeah.
Well, let's thank Lady and Dylan. And thanks to Kelly for getting us together and providing us with snacks.
Yeah.